Alright guys, let's take a look at some Lewis structures and molecular models. So for the pre-lab, you should have gone through all the molecules in the lab below and drawn out your Lewis structures, predicted your electron pair geometry and your molecular geometry, bond angles, and whether or not the molecule is overall polar or nonpolar, and the hybridization of the central atom. So let's go through some of this and take a peek and look at the molecular models of what you should have drawn out. Let's see, get the wrong one up first. Get that out of here. Okay, so your first molecule that you should have made up was this little guy here. We're looking at a Cl2 molecule. So a Cl2 molecule is just a nice little linear molecule. That's the only way you can connect two dots, right, end to end with a straight line in between them. So each one of these green balls, this is how these work, these stick together. Each one of these green balls represents a chlorine atom, and then we've got the bond, the gray bond piece in between them. So we've got a Cl2 molecule. You can tell it's linear, straight line in between the two, which makes it a 180-degree bond angle between the two atoms. And nonpolar, right? So we've got two atoms of exactly the same type. So they have the exact same electronegativity and the exact same pull. Therefore, it is a nonpolar molecule. All right, so that is our Cl2 molecule. Let's look at our next one, N2. So when you drew out the Lewis dot structure for N2, you should have come up with a triple bond between the two nitrogen atoms. So N2 would have this triple bond. So you got three little stretchy bonds there, forming that triple bond and a linear molecule. So each of the ends here, I don't have little plugs in, but they are where your lone pairs of electrons are. So you've got 4 steric groups around each nitrogen atom. So, not 4 steric groups, you've got 2. Excuse me, I said that wrong. You've got 4 places. But you've got 2 groups, you've got this one bond, and then you've got the lone pair of electrons on the end. So nitrogen atoms will tend to form 3 bonds. In this case, it's a triple bond, and have a lone pair of electrons on the end. So again, we've got two of the same atoms straight on from one another, so it's a linear molecule with a 180-degree bond angle, and again, they've got the exact same electronegativity with the exact same lone pairs of electrons on the end. So we've got ourselves another non-polar molecule, and if you were to look at the hybridization of each atom, you would have sp hybridization of each atom here. Next up, we've got IBr. Got, again, a nice little linear molecule. With iodine on one side and bromine on the other, connected with a single bond. Each iodine and bromine have 3 sets of lone pairs of electrons around each one of them, which is a typical bonding pattern for our halogens, 180-degree bond angle, but we would have some polarity to this molecule, right? We've got 2 different atoms, so we've got slightly different electronegativities with each atom. So the degree of polarity would be determined by those differences in electronegativity. If you look at the hybridization of each atom, which generally will only look at the central atom, but in a linear molecule, you would look at the hybridization of each atom. You would say it was sp3 because it's got the bond and then the 3 lone pairs of electrons. All right, let's go on to molecules now, or other molecules, bigger molecules with a central atom. So first up was CO2, carbon dioxide. So here we've got our carbon in the middle. So carbon atoms are going to be black. Oxygen atoms are going to be represented by the red ones. And they've got little holes in them in particular ways for how they tend to bond. So the little black balls that represent carbon have 4 holes to add the bonds in that tetrahedral manner. So you can see it here when you've got hydrogens attached. It's got 4 holes to put bonds in for that tetrahedral bond shape, or molecular shape, I suppose. And oxygen has just 2 on it, where the 2 bonds would normally come out to form the shapes of oxygen, and the lone pairs of electrons would be out there. So anyway, carbon dioxide. You should have gotten carbon as your central atom with two double bonds on each side to oxygen, and then the oxygen, each oxygen has lone pairs of electrons. So it's forced into this linear shape again. To get these steric groups as far away from one another as possible, with 180 degree bond angle. And let's see, we've got an even distribution of our groups here, of our more electronegative atoms, either end to end, and you can kind of cut it in half either way. So we've got symmetry, and we can fold it in half in any way. And we would have symmetry here in this molecule. So the vectors, the vector quantities for the dipole moments within this molecule would cancel one another out, making it a non-polar molecule. And if we look at our central atom, we can determine the hybridization. We've got 2 steric groups around it, so it would be sp hybridized. Okay, that's our carbon dioxide molecule. Next up, water, H2O, dihydrogen monoxide. So this guy is our water molecule. So water has 1 oxygen in the center. Hydrogens will always form 1 single bond. They'll always be on the periphery of your molecules. They won't be on the insides. They don't form more than 1 bond. Remember, it's only got 1. We're only filling up that 1s shell, so we're only going to have 1 bond for hydrogens ever. And the bond angle is about, so we get this shape with our hydrogen, or our water molecule. We've got 2 lone pairs of electrons up here, which is a typical bonding pattern for oxygen, to have either a double bond or 2 single bonds, and then the 2 lone pairs of electrons up in this region, I suppose, more in that tetrahedral shape. So let's see, we end up with a water molecule that looks a little something like this, and we have our electron pair geometry and our molecular geometry are going to be different from one another because of the lone pairs of electrons. So if we look at the electron pair geometry about our central atom, we end up with a tetrahedral electron pair geometry about the oxygen. And when we don't look at those, we end up with a bent molecular geometry when we look at just the atoms. So we have this bent shape left over with this slightly less than 109 degree angle. So in a regular tetrahedral geometry, like in methane, we have 109.5 degree bond angles. However, when we start having lone pairs of electrons here, the lone pairs of electrons take up more space or have more push and squish these bond angles closer and closer to one another, making them smaller and smaller. So that bond angle is less than 109.5 degrees because of the lone pairs of electrons. So it's about 104.5. And we would have a polar molecule. We do not have that symmetry, right? We can divide it in half this way, but if we look at it this way, we do not have symmetry. And if we were to look at our vector quantities, right, we've got these arrows coming this way, coming up. Let me grab a piece of paper. I had plain paper over here. So if we were to look at the vectors involved here, we've got arrows coming this way. So we've got the positive end leading towards the negative. Now those vectors are the same size, but we've got the x and the y components of each vector, and those x components of each, or the y components of each vector in this, depending on which way you set all up your grid, I suppose. The vector component of the vector that leads in this upward direction is going to add one another, where these ones would cancel out. So we end up with an overall polarity of the molecule. We'll put it in blue, kind of like this. So we end up with an overall polarity of the molecule in that general direction. So water is a polar molecule. And the hybridization of our oxygen here is, we've got 4 steric groups, remembering that we've got these 2 lone pairs of electrons, so we've got 4 steric groups, so we'd have an sp3 hybridized oxygen. Right, kick out that water. Let's see what is next. Ammonia, NH3. All right, so here is our ammonia. So we've got our lone pair of electrons here at the top, and then we've got our 3 hydrogens. So we have 4 total steric groups around our nitrogen. So we've got 4 total steric groups, making it a tetrahedral electron pair geometry. And when we look at the molecular geometry, we end up with this trigonal pyramidal. See how it's got this triangle base between these 3 hydrogen atoms? Those hydrogen atoms, but this nitrogen is raised up out of the plane in comparison. So you can see it sits off the table a little bit. So we've got that trigonal pyramidal shape, and you can kind of see how it's got the trigonal base, and it's a pyramid because it comes off a little bit and looks like a pyramid. So trigonal pyramidal with these 3 atoms here and the lone pair of electrons, making these bond angles. This bond angle here, hydrogen, nitrogen, hydrogen bond angle. It's just slightly less than 109.5 degrees. And we would fall into that polar category again. So these are all polar bonds, and they're going to add up. So we have polarity and that negative polarity towards this nitrogen atom. And nitrogen has 3 steric groups around it, so it would be sp3 hybridized. All right, so let's look at our next one. CH4 is methane. Methane has carbon at the center of 4 hydrogen atoms. Like I said, hydrogen will always be on the periphery, on the outside of your molecule, because it's only going to form single bonds. And the farthest, how these hydrogens get the farthest away from each other is in this tetrahedral shape in 3 dimensions, because they are not flat, they're 3-dimensional little molecules. So we have both. We don't have any lone pairs of electrons, so we have both our molecular and our electron pair geometry the same, with both of them being tetrahedral, and the idea of bond angle between the hydrogen, carbon, hydrogen, which is the same for all of them, whichever direction you were to look. Hydrogen, carbon, hydrogen bond angle would be 109.5 degrees. And because all those bond angles are the same, and we'd have perfect symmetry no matter which way we looked at it, all of our vectors would cancel each other out, even though, let's also point out that this carbon-hydrogen bond is considered to be a nonpolar bond since they're very close in electronegativity. We'd have an overall nonpolar molecule. But anyway, let's keep this here. Oh, and our carbon has 4 steric groups around it, so it'd be sp3 hybridized. Let's look at the next one. CCl4, carbon tetrachloride. So again, we have the same shape as we did for our methane molecule, only we have polar bonds now. From the carbon to the chlorine, we have those polar bonds. So all our information would be the same. We've just replaced hydrogens with chlorines, and we have created polar bonds. But if we were to look at all the vectors of these polar bonds, they would all cancel one another out, and we'd have an even distribution of the polarity within the molecule, making it overall a non-polar molecule again. So we have polar bonds within the molecule, however, they cancel one another out. The vectors cancel one another out, creating a non-polar molecule. Okay, let's keep those guys here. Keep those guys here. All right, next one up. CHCl3. All right, so we've basically taken our methane and put 1 chlorine on there, right? So we've got one polar bond within the molecule. So we've still got tetrahedral, about 1 and 9.5 degree bond angles. However, we now have one polar bond within the molecule, and then these bonds are all different. So we're going to have an overall polarity to the molecule, unlike with these two guys here, with our methane and our carbon tetrachloride. We've got an overall polarity with a negative end being at this more electronegative atom or element. 6 1/2 dozen the other. Okay, so we end up with a polar molecule. Again, our carbon is still sp3 hybridized with the 4 groups around it. All right. Next up, we've got CH2Cl2. So carbon is the black one again. Remembering these are hydrogens, chlorines. So we've got 2 chlorines and 2 hydrogens, again in our tetrahedral manner, about 109.5 degree bond angles. And again, we'd have a polar molecule because they aren't going to cancel one another out, just like in water. You can see we've got these 2 polar bonds, the vectors heading the positive to the negative, and they would be additive in this direction. So we'd have an overall polar dipole moment in this molecule with the negatives towards our chlorines. So it would be a polar molecule. Again, lack of symmetry is always a way to look at it. It would not be able to fold it over. All right, so we'd have a polar molecule. Okay, get all those tetrahedral carbons out of here. And bring in another tetrahedral carbon. Yes, so ethane, we've got 2 carbons, 6 hydrogens. So they would come together with both of these carbons, forming a single bond between one another. And our 3 hydrogens on each carbon on the periphery on the outside of our molecule. Look, they're free to spin and move about one another. So kind of free to move that way. All right, so we've got each carbon has 4 steric groups around it, right? So this carbon has 3 hydrogens and another carbon. So it is tetrahedral along with this one. They are exactly the same. And they'd have about 109.5 degree bond angles. So this hydrogen, carbon, hydrogen, or the hydrogen, carbon, carbon bond angle would all be about 109.5 degree bond angles. Again, we have symmetry within this molecule and very low differences in electronegativity. So we'd have a non-polar molecule, and each carbon would be sp3 hybridized. All right, next one. Ethene, C2H4. So when we do our Lewis structure for C2H4, we should end up with a double bond in between our 2 carbons, and we actually end up with a fairly flat molecule. Look at that. So this carbon-carbon double bond in the center here kind of holds the molecule more rigid. Like our ethane, we could spin it and they can move relative to one another, right? Like that. However, when we have a double bond or a triple bond, it kind of holds some rigidity to the molecule and doesn't allow it to spin about that axis. So it's going to stay in its orientation, which if you take organic, you're going to need to know that. So we've got our carbon-carbon double bond in the center, and we end up with our electron pair geometry and our molecular geometry, again, the same. There aren't any lone pairs about our carbon atoms, so we have a trigonal planar. You can see how it's kind of planar. It's flat. Like I said, it was a flat molecule. It's all in the page of the paper. So if you were to draw it like this, you kind of end up with a very accurate representation. So we've got trigonal planar. So if we think of, so we've got trigonal planar. So each of these bond angles are about 120 degrees. So this hydrogen, carbon, hydrogen, or this hydrogen, carbon, carbon bond angle are all the same at about 120 degrees. And we have a non-polar molecule. Each carbon has 3 groups around it, so it is sp2 hybridized. All right. C2H2. I just used shorter hydrogen bonds here. There's still hydrogen bonds there, but I was running out of the longer bonds. That's all that's different there. I was running out of the longer plastic pieces. All right, so we would end up with a triple bond in between our two carbons, right? So that's the only way to make that Lewis dot structure reasonable. We get a triple bond. It's, look at how much shorter they get. It's kind of funny how it's so accurately represented, right? So we get this shorter bond distance. We have a tighter pull there. And again, it's we can't spin about that axis. So we have our triple bond between our two carbon atoms. We get our hydrogens on the end, and we end up with a linear molecule. Both electron pair and molecular geometry are linear. And in our linear molecules, we have 180 bond degree angles because they're in a straight line. And it would be a non-polar molecule. Each carbon atom would be sp hybridized. All right, next, HCN. HCN looks a little something like this. We've got our carbon atom and our nitrogen atom with 3 bonds in between. Look at the nitrogen atom having its lone pair of electrons out here. So you should have a lone pair of electrons here on the nitrogen atom, a triple bond between the nitrogen and the carbon, to a hydrogen atom hanging out here on the end in a linear fashion. So we end up with a nice little linear molecule again. Linear molecules have a 180 degree bond angle. We do have some polarity to this molecule, right? Nitrogen is more electronegative than carbon. So we have polarity in the molecule, the more electronegative element being nitrogen. It's closer to fluorine. And our carbon atom would be sp hybridized because it has 2 steric groups around it. What's up next? Methanol. CH3OH. So our methanol. That is this guy right here. So our carbon is at the center. We've got 3 hydrogens out in that tetrahedral manner. And then we've got a single bond to our oxygen, and then a little hydrogen stuck out here being our alcohol functional group. So let's take a peek at this guy. Oh, and then oxygen will always have its, not always, but yeah, most of the time, have its 2 lone pairs of electrons out here. So we've got 2 lone pairs of electrons here on the oxygen, 4 single bonds around our carbon to our hydrogens. So our carbon will have its molecular geometry and electron pair geometry being the same, both of them being tetrahedral, 4 steric groups, all 4 of them being atoms. And if we look at our geometry around our oxygen atom has these 2 lone pairs of electrons out here, so its electron pair geometry is tetrahedral. However, its molecular geometry is bent. We only have 2 atoms around there, so that's all you have left. So let's look at some bond angles. It asks for our HCH bond angle, so our HCH bond angle in this tetrahedral molecule would be about 109.5 degrees. And our HOC bond angle, so this one right here, I looked at that, I was pointing it out wrong. HOC bond angle, because of these 2 lone pairs of electrons, is going to be less than that 109.5 degree bond angle because of the lone pairs, squishing this bond angle smaller than that. We have one of those that is not like the other, so we have a polar molecule with a very electronegative element here. Our carbon has 4 groups around it, so it is sp3 hybridized. Oxygen, don't forget, 2 lone pairs of electrons, is also sp3 hybridized. All right, let's take a look at part B. N2O. So we've got our 2 nitrogens in blue and our oxygen in red. Our 2 nitrogens are joined together by a triple bond, a lone pair of electrons here on this nitrogen, single bond to oxygen, and 2 lone pairs of electrons on our oxygen, giving us the best formal charges for this particular structure. Gives us the best formal charge options. with a +1 on this nitrogen, a 0 on this nitrogen, and a -1 on our most electronegative atom being oxygen. Anyway, so we get a linear orientation of our molecule. 180-degree bond angles go along with those linear molecules, and we have polarity in this molecule with the most electronegative element being on the end. And our nitrogen with 2 steric groups around it is sp hybridized. SO2 looks a little something like this. We've got our sulfur at the center. Our sulfur atom at the center, and then we have our 2 oxygens with double bonds and a lone pair of electrons up here. So we've got our lone pair of electrons, 2 sulfurs double bond, or 2 oxygens double bond, each of them double bonded to our sulfur in the center. Lone pair of electrons, so we have 3 steric groups around that sulfur. This particular arrangement gives us the least amount of formal charges on our elements, all of them being 0, or atoms, I suppose. So we have 3 steric groups. We have trigonal planar. One of those steric groups is a lone pair of electrons, so our molecular geometry is bent. We've got 120-degree bond angles, and in our bent molecules, we have polarity within our molecules, making our sulfur sp2 hybridized. All right, HNO3, nitric acid. There's our little nitric acid molecule. All right, so our nitrogen is at the center of our nitric acid HNO3 molecule. Nitrogen oh, I made a mistake. Why do I have that hydrogen there? I have too many hydrogens. There we go. That's better. All right, so that is it. Now that I have the appropriate amount of oxygens. So we got our nitrogen at the center. It is double bonded to 1 oxygen atom. This oxygen atom will have 2 lone pairs of electrons out here. This oxygen atom here, single bonded with 3 lone pairs of electrons and a formal charge of -1, a formal charge of +1 on the nitrogen. Another single bond to this oxygen, but it also has a hydrogen, your acidic hydrogen, and then we have 2 lone pairs of electrons here. My nitrogen will have both electron pair geometry and molecular geometry of trigonal planar. See, it forms a little triangle. Boop, boop, boop. Trigonal planar. Let's see, we're going to look at this oxygen here. If we look at the electron pair geometry of oxygen, don't forget we have 2 lone pairs of electrons hanging out here. So we have tetrahedral electron pair geometry. However, we have bent molecular geometry. Our oxygen, nitrogen, oxygen bonds are 120 degrees. And our hydrogen, oxygen, nitrogen bond is less than the 109.5. We definitely have some polarity within this molecule. And our nitrogen is sp2 hybridized. And then we have a couple different hybridizations depending on which oxygen you're looking at. This guy would have sp3 hybridization. Right, that was part B. Okay, part C. Let's look at some polyatomic ions. So let's see, most of these have extra electrons added into the structure because they're polyatomic ions. All right, so first up is our hydroxide ion, our OH minus. OH minus will look a little something like this. Hydrogen always only forms single bonds, so we've got a single bond from the oxygen to the hydrogen. The oxygen will have 3 lone pairs of electrons to complete its octet, an overall -1 charge, so we've got a linear geometry in the overall of the molecule. 180-degree bond angle. We've got 3 lone pairs of electrons and the bonding hydrogen over here, so our oxygen is sp3 hybridized. Cn minus ends up looking a little something like this. We've got a triple bond between my carbon and my nitrogen, and 2 lone pairs of electrons right here and here on the end of each. So lone pair of electrons on the nitrogen, a lone pair of electrons on the carbon with an overall -1 charge. We've got linear geometry about this molecule, 180-degree bond angle, and each my carbon and my nitrogen are sp hybridized. All right, so we have to change up our color scheme. Normally chlorine is these little guys, but it only lets us do single bonds with them, and it doesn't take into account hypervalency. So we're going to play with the gray one and pretend that is our chlorine for now. So for our chlorite, oops, let's fix this. We want that for the chlorate. Put that back there. Our chlorite, ClO2. There we go. Ah, get in there. Okay, so our chlorite ends up a little something like this. We've got our chlorine at the center, double bonded to one oxygen atom, single bond to the other oxygen atom, and 2 lone pairs of electrons. Putting a -1 formal charge on the single bonded oxygen and 0 formal charge on this oxygen and the chlorine, giving the chlorine tetrahedral electron pair geometry and bent geometry to the molecule. This bond angle is less than 109.5 degrees, and my chlorine is sp3 hybridized. All right, so now I need to add in, for chlorate, I need another oxygen. And let's see if I can make it look right. There we go. Here we go. All right. It's going to be a little hard to see on the cameras. I don't think it'll look great, but we'll try it. It still looks the same. Okay, so our chlorate, ClO3 minus, ends up looking a little something like this when we take into account formal charge. Distributes the formal charge the best, ouch, in this manner. So we've got our chlorine at the center, double bonded to 2 oxygens, and single bonded to 1 oxygen, and a lone pair of electrons on the chlorine, giving the chlorine tetrahedral geometry and tetrahedral electron pair geometry and trigonal pyramidal molecular geometry, about less than 109.5 degree bond angle, and sp3 hybridization. Okay. What do I have next? Carbonate, CO3 minus, ends up looking something like this. So the carbonate has a double bond to the oxygen, 2 single bonds to the other oxygens, 3 lone pairs of electrons on each of these oxygen atoms, and 2 lone pairs of electrons here on this, giving the carbon trigonal planar electron pair and molecular geometry with 120 degree bond angles and sp2 hybridization. Ooh, okay. What was I gonna do? I had a plan for how I wanted to do this. All right, so let's see. I'm actually gonna, let's pretend I didn't just use the same molecule, but now we're gonna pretend this is a sulfur atom. Okay, so I don't have to switch around my molecule. In this sulfur atom for our sulfate ion, so that's what we're moving on to, we end up with a similar Lewis dot structure where we have a double bond to 1 oxygen atom, 2 single bonds to each of the other oxygen atoms, and the same types of lone pairs on our oxygen atoms. So 3 lone pairs of electrons and lone pairs of electrons here, 3 pairs of lone pairs of electrons here, and 2 lone pairs of electrons on the double bonded oxygen atom. However, the sulfur atom in the center has a lone pair of electrons as well, unlike the carbon from the carbonate before. So this is, as a sulfur atom, has a lone pair of electrons on that center atom, giving it tetrahedral, which isn't great to see because I don't have the right ball to use, giving it tetrahedral geometry, electron pair geometry, and trigonal pyramidal molecular geometry, and about 109.5 degree bond angles, and sp3 hybridization for that sulfur atom. All right, SCN thiocyanate. We end up with a linear molecule. We've got our sulfur atom, single bonded to our carbon atom, which is triple bonded to our nitrogen atom. Our nitrogen atom has a lone pair of electrons. The sulfur atom has 3 lone pairs of electrons. We end up with a linear molecule with 180 degree bond angles and sp3 hybridization of our carbon atom. Let's see, what is next? You are next. Formate. The formate ion. So we end up looking a little something like this. We've got a carbon atom at the center, double bonded to an oxygen atom that has 2 lone pairs of electrons, single bonded to the other oxygen atom, which has 3 lone pairs of electrons, and a single bond to our hydrogen atom, giving our central carbon atom electron pair and molecular geometry that is trigonoplanar with 120 degree bond angles and sp2 hybridization. And last but not least, our NO2 plus. Our NO2 plus will end up looking a little something like this. So we'll have our nitrogen in the center, double bonded to each of our 2 oxygen atoms. Each of our 2 oxygen atoms will have 2 lone pairs of electrons. We have an overall positive charge to the molecule, which will be linear, have 180 degree bond angles, and our nitrogen would be sp